Kia ora. All right, let's start our last task for this week, which is looking at the alcohols and also talking about the last type of isomer, which is those optical isomers. Optical isomers are not limited to alcohols. I just stick it in this lesson because the alcohol lesson isn't very long. So just FYI with that. Cool. All right, so success criteria, you should be able to do the naming and stating the properties of alcohols, and we should have now finished all of those isomers because we can do these optical isomers, which can also be known as stereoisomers or enantiomers. Cool, so let's start with the alcohols. So alcohols contain the functional group of OH. We've talked about this in the previous lessons as well, but I'll give it in more detail. So with these alcohols, just keep in mind that the general formula is pretty much the same as an alkane. The only difference is that we now add an oxygen to it. So you can either keep the formula the same as 2N plus 2 and then have an O, or you can do it in this format here, and it's just stating the hydrogen is specifically attached to an alcohol. You might also see this written as a shorthand, so an OH with the R, and the R in general just refers to as some sort of carbon chain. It's usually just a placeholder. Cool. Any alcohols with more than 3 carbons can form structural isomers. If I have 1, then obviously it's on carbon 1. If it's 2 carbons, then it can be either on 1 or 2. Unless I start having multiple alcohols, then I need to specify which one's on. Cool. So naming is the same kind of rules that we've talked about previously. Find the parent chain, that's the longest chain, but whichever you find is the longest chain, it needs to have the function group attached to it. Identify any of the branches. When it comes to numbering the chain, you're going to take the number assignment to give the alcohol the lowest group, and the branches get whatever they get. You have 2 choices when it comes to alcohols and how you name them. You can either change the suffix to OL. You can also have a prefix version instead, and you then have hydroxyl as the beginning word, like you would with the haloalkanes. Either or is correct. If you do use the hydroxyl prefix version, then the suffix you're going to use is just the alkane ending. The reason you tend to use, or the reason why we have a prefix version as well as a suffix version, is that when we name more complicated molecules, you might have a function group that only exists as a suffix, and so you have to then name the alcohol as a prefix. But we will see this later, so don't worry about it yet. And then same thing with the rules. If you have multiple alcohol function groups, you state all the numbers and you state di or tri, etc. And when it comes to the naming order, you do branch position, branch name, parent name, and then where's the location of the alcohol, and then the OL ending. If you are naming the alcohol as a prefix, then you just put it into alphabetical order. So here are some properties with them. We start seeing some more solubility in water, and we get some polarity, and that's because of that hydroxyl group there. On top of it having that hydroxyl group, it can also do those hydrogen bonds. So remember, with those hydrogen bonds, we need the hydrogen attached to something very electronegative, such as nitrogen, oxygen, or fluorine. If it's attached to any one of those 3 things, then it's able to form hydrogen bonds, which is a relatively, I wouldn't say relatively, it's the strongest of the intermolecular forces, so it's quite up there. So yeah, there is then going to have those weak intermolecular forces to the molecules. If we have a polar molecule nearby, it will make a permanent temporary dipole-dipole. If it's not polar or any other molecule, it'll be instantaneous. We'll talk about this more in thermochemistry. For small alcohols, that hydrogen bonding will greatly affect its physical properties. It will be soluble in water. That's why ethanol can be mixed into various drinks, and that's why you have ciders and things like that. But obviously the larger it gets, the longer that nonpolar tail is, and that's going to decrease the solubility as we've seen in the other molecules. Alcohols cannot conduct electricity. Remember that hydroxyl group isn't donating or accepting protons. It doesn't act as an acid or a base, so it won't be conductive. Melting point is obviously, melting and boiling point is going to be higher because we have the hydrogen bondings, and that requires a little bit more energy to break. Because of that, it also tends to be a liquid at room temperature. So if you're comparing carbon chains of the same length, the alkane versus the alcohol version will have higher melting and boiling points. These guys are soluble because of that hydroxyl group, but the solubility does really depend on the length of that chain. Like I said, the longer that chain becomes, the more nonpolar it is. Alcohols are really commonly used in industry for perfumes, and that's because you have molecules that have both a polar and non-polar component to it, and thus you can mix together stuff that is polar and stuff that is non-polar to make a solution that actually mixes together. And this is what I mean by the polar end and the nonpolar tail, and depending on that length of that nonpolar tail affects the overall solubility. But if we're trying to make a perfume and I have things like water, well, this will be able to attract the water, and this will be able to attract the nonpolar chemicals that I'm using. So 1 to 3, soluble. 4, still kind of soluble, but not as soluble. Anything up to 5 is starting to lose that solubility, and anything past that point is no longer soluble. So just FYI. I also think it's important to point out some important specific organic molecule, alcohols. The first one being ethane 1,2-diol. Basically, it is 2 carbon length, and each carbon has its own alcohol. These guys they are similar to ethanol, but their melting point and boiling point are slightly higher, and that's because you have that extra hydroxyl group. And so this is then mixed into things such as antifreeze because it has that higher melting and boiling point. So we see this a lot in car radiators and when we de-ice wings. Glycerol is another specific molecule that you commonly come across, and you'll see this a lot when we start doing esters. In this case, it is the common name for a propane with 3 alcohol groups, and it's a triol in that case, and it's on carbon 1, 2, and 3. So each one of these carbons has a alcohol group, and each one of them are then going to be able to form an ester bond, which we'll see in a later lesson. Cool. This glycerol is often a byproduct with alkaline hydrolysis. So whenever we're trying to break apart animal fats and oils, we tend to get this as a byproduct. And you can also react that with nitroglycerin, and you can react that with concentrated nitric acid to make nitroglycerin, which is an explosive. And then glycerol can be used to be made in makeups and in resins as well, because it can do a lot of binding. Here's a fun fact. The Nobel Prize actually has some dark origins. Alfred Nobel got his money by making dynamite. He stabilized the nitroglycerin. So basically taking this molecule, reacting it with the nitric acid, and making a stable form of nitroglycerin that you can use as an explosive. Cool. Like we were talking about with the haloalkanes, the alcohols can do those structural isomers as well, and it just depends on where that hydroxyl is located. And again, it follows the same rule of primary, secondary, and tertiary. So that's just something to remember and know when it comes to classifying. And another kind of hint when we're classifying primaries, you'll see 1 in the name. Secondaries, you will often see 2 or 3 in their name. And tertiaries, what you're looking for is the functional group with a branch with the same number, because they're obviously both sharing that carbon there. Cool. The new thing we then have to talk about is optical isomers. So optical isomers, also known as stereoisomers, also known as enantiomers, are a type of mirror image optical isomer. So basically you have two molecules, but one of the molecules looks like it's been reflected in a mirror. And in fact, these are two different molecules. They are not the same. That's why we note them as D and the other one is L. These cannot be superimposed. So regardless of how I rotate these molecules around, there is no way I'm going to get the exact same molecule. So let me show you this on the document camera. I've built some so you can see it. Oh, there goes my playlist. We don't want that. I don't know why my document camera keeps crashing. That's not cool. Do I need to restart you? We're gonna pause this and fix it. Cool, now I got it to work. All right, so here is one of my molecules. In that molecule, we can see that I have my carbon atom. I have an alcohol group, that's the oxygen with the one hydrogen. I have a hydrogen on the top here. I have a methyl attachment here, and then I also have a nitrogen amine, which is that blue, and has the two hydrogens attached to it. The main thing I'm looking for is that I have a carbon and has 4 different things attached to it. Now this is obviously one version of it. If I do a mirror image, that's what it would look like. So if I have a mirror right here, this is what the reflection looks like. The thing about these optical isomers is that no matter how I move and rotate around these molecules, they will not be the same. So in this case, when I look at it like this, side by side, they're obviously in different locations. And if I move this around, well, that's still not the same molecule. If I move it that way, it's still not the same molecule. There's no way I can move this around for that molecule to be exactly what I see on the other side. So yeah, that's what it means by non-superimposable. And I can't, like, every time I try to line it up, there's no way for me to line it up. So that's what I mean by mirror images. The other way to think about it is your hands. Your hands are mirror images of each other. They're non-superimposable. There's no way I can move my hand around so that way I am looking at it exactly the same. Like, even though I have my fingers lined up the same way, it's not the same thing because I have the palm versus the face of the hand. So if I do that, like, yeah, mirror images. So I hope that makes sense. It's kind of one of the harder things to communicate across. But yeah, that's what we're looking at. Mirror images of each other. There's no way we can move it around that it's to create the same image. This is what you'd see when you're drawing it in 3D. So what you would do on the assessment is you draw one organic molecule as your tetrahedral, just like you did for structure and bonding. And then what you're going to do is draw the mirror image of it. So basically you flip it around. And when you do that, you still have the dashed lines and it's still connected to the same molecule. I'm not sure if I should do an example showing how I would draw it or if you guys are okay with that. I feel like I should draw it because I find that every time students struggle with understanding how to do it. And I'll just do the molecule that I had made. All right, so draw the first molecule. So this is the one that I had here, that way. So that one's within plane. That one we'll say is also within plane. This one's coming out at me, so we're using that bolded line. And this one is going behind the plane. You can't see what I see. There we go. Can you see everybody? Do we need to zoom it out? There we go. So this is the plane, within plane, behind, in front. All right, so that's one mirror image. Then what I need to do is flip it around. So when I flip it around, what I am doing is I am doing the dash, doing the bold, like that. So basically I've taken that and flipped it around, and you are still attaching the same things to it. Like that. That's how you do it. Basically, the easier way to kind of remember it is you draw these two the same, and what you're doing is you're flipping that around. So I flipped that one to this side and I flipped that one to that side. I don't know if that makes any more sense, but don't worry, you'll have time to practice that. Cool. So with these optical isomers, in order for them to occur, I need to find what is known as a chiral molecule, looking for that chiral carbon. So basically, I'm looking for a carbon atom that has 4 different things attached to it. If it doesn't have 4 different things attached to it, it doesn't form optical isomers. And then you get these 2 different versions, and we label one D and one L. You're not going to be expected to know which one's D and which one's L. They have similar chemical and physical properties. They'll do similar chemical reactions. The only thing that we can really use to distinguish them is polarized light. So they rotate in opposite directions, and that's an important thing to know because they often ask that question, how would you distinguish them? And you'd say, I would distinguish them using polarized light. They would rotate in opposite directions. If there's an equal ratio of both optical isomers, then we don't see any optical activity. With this question, make sure you're layering it. So explaining what a chiral carbon is, explaining, which carbon in that molecule is the chiral carbon, drawing the molecules correctly, and explaining that, they are mirror images of each other and they're non-superimposable are other 2 keywords you should be dropping down. What I should also add that's interesting about these optical isomers is because they are mirror images, they can affect how they fit into proteins and things like that, and how they fit with metabolism. One fun fact is that with the amino acids, a lot of them are optical isomers, and we only use one version. I think we use the L version in our bodies, whereas different organisms use the D version, and some organisms can use both. The other thing from a pharmacologist perspective is that these optical isomers can be important with the metabolism of drugs. In some cases, one optical isomer is the active drug that's good for us, and the other optical isomer is a toxin. And we need to make sure we separate these 2 optical isomers before we distribute the drug. So just some interesting things about optical isomers. They do actually play a major importance in the bigger scheme of things. All right, goodbye. Really good work today. So you should know your alcohols now, and you should know all of the isomers. Optical isomers is obviously the new thing, so you'd expect that to be the question on the exam. Now it's time to go to your Mahi choice. Remember, those are all listed on the Google Classroom. I do not expect you to do all of it. Or not listed on the Google Classroom, listed on the Google site, available on the Google Classroom. I do not expect you to do all of it. It is a lot. It is there for differentiation and to give you guys some choice. And that's all for this week.